Thank you so much. Yeah, so I'm Andrew Guntark. I'm a software engineer at NVIDIA in the Compute Debugging Tools team. So let's start out with an introduction to the NVIDIA debugging toolchest. So on Polaris, we provide something called the NVIDIA HPC SDK. This is a comprehensive suite of compilers, libraries, and tools specifically designed for the HPC workflow. You can read more about what's included in the HPC SDK at this link. On Polaris, this is provided to you by the NVHPC module. By default, the NVHPC/21.9 module is default, and bundled with the HPC SDK is a debugging tool chest. So two tools I'm going to talk to you today about are CUDA-GDB. This is an interactive thread-based debugger, and the Compute Sanitizer, which is a functional correctness checking suite. I also want to mention there is a API debugging capability in the Insight Compute Profiler. I'm not going to go into its usage. It's GUI-based. It allows you to step through CUDA API calls, and you can examine the call stack and the functions that are passed in. It's out of scope for this presentation, though. So let's start out with CUDA-GDB. So what is CUDA-GDB? It's based on the familiar GDB debugger. So there's a lot of people who come from the CPU world, and maybe they've developed on Linux, they've used GDB in the past. So there's a real ease of use here. Users are already familiar with how to use GDB. And we try to provide a GPU debugging experience that is, it's very logical to what you're used to with CPU-based debugging. There's existing C, C++, and Fortran support that we build on top of. And there's a seamless debugging experience between both the host or CPU and device or GPU debugging. So you can have a single tool and have a single session where you can debug both your CPU, the CPU part of your application and the GPU part of your application without switching tools. We have support for CUDA, Optics, OpenACC, OpenMP, and any other middleware that's going to eventually compile code down to CUDA. There's support in CUDA-GDB form. We support SAS disassembly, so if you want to do SAS debugging, you can do so. And there's various command extensions unique to CUDA-GDB that I'm going to talk about in this presentation. It is an interactive command line interface-based tool, so you are driving the tool as you debug your workflow. And it provides reactive debugging of CUDA kernels. What do I mean by reactive? It means you're reacting to something that could be wrong in your application. So this could be a CUDA runtime error. You could have a hardware exception that's occurred and you want to debug it. Or there could be logical errors that are producing incorrect results in your application, and you want to kind of lift up the hood and see what's going on in your program state. We also provide support for post-mortem debugging with core files. Core dump capture is enabled via environment variable. I'll talk about that in a future slide. In the environment, these are off by default, so you have to enable this feature to get a core dump. So on Polaris, CUDA-GDB is provided in your path by default. It's in NVHPC/21.9. So if you wish CUDA-GDB, you'll find the default CUDA-GDB is in your path. Here's a link to the latest documentation. The documentation also has a specific section I want to call out called tips and tricks, where you can kind of go to and find some edge cases maybe you didn't think about, or useful recipes. And we're trying to expand this over time. So as we find more recipes that we think end users would find useful, we're adding them to this section. Getting help, we do have a developer forum, so you're free to sign up for an account and interact with the CUDA-GDB developers directly. All right, so let's talk about quick start. So the first thing you need to do when you want to debug your application is you need to recompile your app for debugging. When you're compiling with NVCC, this means you need to provide a lowercase g for host or CPU debugging, and you need to provide a capital G for device side debugging. And you can see here's putting it together in a single NVCC invocation. The reason we split this apart is sometimes you know the problem is either on the host or device. You want to run either or with optimizations enabled. So maybe you know there's a device issue. I just want to enable debugging on the device. Host side, I want to keep optimized so I have fast running code. So you can do so. It's up to you. You can also use line info to allow for optimized code debugging. You do have to be careful here though, because when you use line info, it will lack debug info sections. What do I mean by that? I mean, there's no symbolic debugging. So if you break in the middle of a kernel and you try to examine the state, maybe you have a symbol named foo that you know you've written in your code, you cannot do so because we don't have debug info present. Also, debugging of optimized code can be a challenging experience. So the compiler is allowed to do all kinds of clever things and rewrite your code in unexpected ways. So what you are expecting might not be what's actually executing. Also check your compiler manual. So if you use a different compiler other than NVCC, the command line arguments will vary by compiler. So it's what I gave you here is just for NVCC. It's different for each and every compiler. Pascal Plus GPUs have an improved debugging experience. It's a lot of scope for this presentation. I'm not going to go into all the details. There is feature support listed of what has changed in the CUDA-GDB manual. As new hardware architectures come along, we advance the debugging experience for end users. Some HPC features of interest. Multi-GPU debugging is supported on the same node. What I mean by this is if you have a single application that is making use of more than one device, you can debug that application in a single CUDA-GDB instance, so you'd be able to see all the kernels that are launched on every device. If we also have support for multiple CUDA-GDB instances that can debug multiple processes running on the same node. So if you have multiple A.outs that are sharing the same GPU, you can fire up multiple CUDA-GDBs, attach onto each one with a unique CUDA-GDB instance, and debug each application side by side. We do have limited support for CUDA multiprocess server or MPS. I'm not going to go into the details, but you can follow them at this link if you want to learn more. You can use the CUDA visible devices environment variable to select which GPUs are available to the application. So this is important if you're going to run a new application under CUDA-GDB control. You can set CUDA visible devices to force that inferior process onto a particular device. If you don't care, you can just run with default. I also want to call out the CUDA lazy loading feature, which can speed up debugging time significantly. We've seen 10x or more. This is going to be especially important for debugging HPC applications. This feature requires CUDA Toolkit 11.8 or newer, or the CUDA driver R5 and the CUDA driver R520 or newer. This is not installed on Polaris today, but at some point I suspect that this version will be installed. You enable the feature by setting the CUDA module loading environment variable to lazy. And what this does is defer loading cubins until their first use. So if you have let's say a large math application or large math library that has n different variants of a kernel, but you're only going to call one variant of that kernel at runtime, it defers loading all n variants of the cubin at runtime. So you're just going to load that one cubin that's actually going to be used, and we save time on parsing debug info. There's more information listed here on this feature if you want to read up on it. CUDA-GDB uses tempter to write temporary files. We default /temp if tempter is unset. And we also require the directory be writable. This is a kind of you have to pay attention to this with QSub. A lot of times when you start a new QSub session, you will set tempter for you, and you have to make sure that that location is writable. Also, you need to make sure that it's the same for both the application and CUDA-GDB. So let's say you've launched your batch job, and then you try to SSH into the compute node where your application is running, try to attach on with CUDA-GDB. You might find it a failure because the tempter Q subset is different than the tempter that is being used by CUDA-GDB. All right, let's go over some terminology. It's important for using CUDA-GDB that we exposed to you. So I'm going to assume that you guys are all familiar with the CUDA programming model. So this is just a very high-level review. We do expose both logical and physical concepts to the user of CUDA-GDB. So on the logical side, what I mean is things like kernel, block, and thread. And on the physical side, I mean things like device, SM, warp, and lane. So with a kernel, it's a function that's going to be executed in parallel on the device. It's executed as a grid of blocks of threads specified by the triple angle bracket syntax. A block is going to consist of threads, 10, 24 threads max in a block. It's a three-dimensional coordinate to define the position of the block. And we call these 3D coordinates dim3s, and the name is block IDX. And this block IDX is bound by grid dim. And then finally, we have thread. This is the smallest unit of work. Again, three-dimensional coordinate. There's a dim3 called thread IDX, and it's bounded by block dim. On the physical side, we have a device. This is a CUDA-capable GPU. It's comprised of many different SMs. SM stands for streaming multiprocessor, which is going to execute blocks in warp-sized chunks. And a warp is a group of 32 lanes or threads. And a lane, of course, is it's the core that executes a single CUDA thread. Let's talk about CUDA Focus. So most CUDA-GDB commands apply to a single thread in focus. This can be either a host thread, so a CPU thread, or a device thread, a CUDA thread. So you're only going to focus on a single thread, not a group of threads, just a single one. Breakpoints or exceptions that are hit inside a CUDA kernel will automatically switch to the device focus. So you'll see a message like this, what you see in the green box here. So we'll print out switching focus to CUDA kernel 0. So that's a kernel identifier. It's a logical concept. This is unique to CUDA-GDB. It's an identifier that we assign sequentially, and it's going to be unique across all devices. So every device or every kernel will have its unique identifier. This begins at index 0. Then we'll see a grid identifier. This is assigned by CUDA. Again, it's logical. It's unique per device. So if you have kernels running on multiple devices, you might see a conflict in the grid ID. This begins at index 1. And if your application is using CUDA dynamic parallelism, you can have negative grid offsets for child launches. Then we have a block identifier. This is going to be the 3D coordinate for a block, the thread identifier, which again, 3D coordinate. Then we have the physical identifiers, which is going to be device, SM, warp, and lane. You do have to be aware of divergent thread behavior when you're debugging your application. So what I mean by this is consider 2 or more threads in the same warp that are executing different instructions. So for example, we have an if-else body. Maybe half the threads will go down the if branch, the other half will go down the else branch. So in CUDA-GDB, we have a concept of an active lane mask. This corresponds to threads that are currently executing device code at a given PC. And then we have a divergent lane mask. This is going to be threads that are waiting or have completed at the given PC. You can use InfoCuda commands to query CUDA-enabled GPU activities. So I'm showing help InfoCuda. This shows all the subcommands that you can use, that you can pass to InfoCuda. Help command is really useful. If you type help followed by a command name, it will show you more information about how you use that command. I'll go over a few of these InfoCuda commands in following slides, but I do want to note that output from InfoCuda, if it's marked with an asterisk, that means that the range contains the focus CUDA thread. So we'll start out with InfoCuda kernels. We'll display a list of all the kernels that are on the GPU. And again, you can see that there's a asterisk here because we only have one kernel present, and the CUDA thread that we currently are focused upon belongs to this kernel. InfoCuda blocks will display all the list of all the active blocks in the focus kernel. It's from a starting index to an end index, count number of blocks within that range, and then the state. InfoCuda threads, this displays the active threads in the focus kernel. So this is similar to the blocks, but we're adding threads, the thread concept on top here. So you can see that there's a count number of threads that are in that range, the virtual PC, and then the file name and line number corresponding to that PC. If you want to obtain the current Cuda Focus, so what CUDA thread I'm currently focused upon, you can use CUDA commands. So here I'm saying CUDA kernel block thread. I see we're focused on kernel 0, block 1, thread 3. So CUDA thread focus, so what CUDA thread you want to focus upon is controlled with CUDA commands. If you want to find information about the CUDA activities, you use InfoCuda. If you want to control focus or figure out what your current focus is, you use CUDA commands. This will set focus to a single CUDA thread. So we're not setting focus to a set of threads, rather just a single CUDA thread. And some commands apply only to the thread in focus. So if you're trying to print local or shared variables, printing registers, printing stack contents, etc., that's all going to apply to the CUDA thread that's currently in focus. Some quick examples: if you want to change the thread, you can say CUDA thread 5. That's going to switch to thread 5. Note the block will stay the same, so whatever block you're currently in focus, that's inherited, and you're going to switch to thread 5 within that block. And you can also specify which block and thread, or you can specify the full 3-dimensional coordinates if you desire. So let's talk about some execution control basics. There's 2 ways to get control. There's the run or attach. So if you're going to run, that means you're going to start a new process or a new application that's under CUDA-GDB's control. You need to provide the name of your a.out. So in this case, it's my application, my_application. And then when I type run, it's going to start a new process. Attach means you're going to attach onto an already running process. This can be a CUDA process, so it could be executing CUDA code. But what you do is you provide the PID. So the host side PID is what you're going to attach onto. You can exit the debugger with quit. Note that when you do exit, applications that you've run are automatically killed if they're still running, and applications that were attached and you're still attached onto are detached by default. You can resume application execution with continue. So something to keep in mind here is when you're continuing it, you're not just continuing the thread in focus, rather you're continuing both host and device threads. So even if you're focused on the device, on the CUDA thread, when you issue continue, it's going to continue the device side as well. You can interrupt execution with Control-C. So if your application is executing, you don't have a CUDA-GDB prompt, you want to get control back, you can issue a Control-C, and that's going to halt both host and device threads. Let's talk about stepping. So when you step, you need to kind of consider a few use cases here. You need to consider, do I want to step at the source level? So my high level language, do I want to step to my next source line? Or do I want to step at the assembly level? Do I want to step to my next SAS instruction? You also have to consider, do I want to step over or into function calls? So if you're going to step over, it means if you have a function call, you don't want to follow execution into that function call. You just want it to step to the next source line in the current function that made that function call. Into function calls means you're going to follow. So you want to follow the function call and see what's going on in that function. Device stepping behavior is a lot like host. So if you're used to stepping in GDB, it's the same exact experience on the device. Or very similar experience. So if you want, again, there's a nice table here. If you want to step over functions, use next for source level, or next I for assembly, and then into, you're using step or step I. Let's talk about some stepping behaviors. When you single step on the device side, you're going to advance every active thread in the warp. Divergent inactive threads are not going to make forward progress, but you're not just stepping the thread that you're focused on. You're stepping every thread in that belongs to that warp. Kernel launches are asynchronous, so you cannot step into a kernel launch from host code. So you could think that, well, if I have a kernel launch and I want to step into it from the host, I should be able to. Unfortunately, we don't support that. So if you do want to follow into your GPU code, you need to set a breakpoint or use the break on launch command, which I'll cover in a future slide. Stepping over barriers. So an example here is like if you have sync threads, if you want to step over that, we'll allow you to, but we do resume execution of all warps executing the same block. So this is a block level synchronization primitive. In order to make forward progress, every thread in the block needs to enter that sync threads. And so the debugger will, behind the scenes, allow those other threads to make forward progress. Setting breakpoints. Symbolic breakpoints. So if you want to set a breakpoint on a function name, or if you're writing C++ code, you have a namespace or a class, and you want to set a breakpoint on either a function, that namespace, or a method in that class, you can do so. Line breakpoints. So if you have a file name followed by a line number. Address breakpoints. So if you want to set a breakpoint on an explicit address, maybe you know the address where an exception occurred and you want to run to that point, you can do so. And then you can also use conditional breakpoints. You have to be a little careful here because the condition part is executed on the host every time the breakpoint is hit. So if you expect this breakpoint to get hit a whole bunch of times, it could be slow. So you'll have to let it run for a while before your conditional evaluates true. we're not evaluating that conditional on the GPU. Kernel entry breakpoints. So this is the break on launch command I talked about earlier. This is used to automatically break on kernel launches. So you will get at least one thread in the kernel will hit this breakpoint, and it's a good first step if you don't know where to start. So if you just want to debug every kernel launch, you can do so by setting this to break on launch application. Info break. So this is useful for viewing the status of breakpoints. Some things to keep in mind is breakpoints can be pending. Breakpoints can be set at multiple addresses, and the locations of a breakpoint can change during runtime. So as an example here, let's say I just break on main. This is going to be a host side breakpoint. This is before I've started even executing my application. We're set at a strange looking address here, so BDAA. That's an unrelocated address, so we don't have relocations applied. So when we run, then that address will be, we will get those relocations, and the address will be automatically updated under the covers. You don't have to have any involvement here as a user. Breakpoint resolution. So when you set breakpoints in CUDA code, sometimes they can be inserted as pending until the Cuban has been loaded. So before we've loaded a Cuban, we're missing most CUDA symbols. So if any function calls, we won't have a symbol for it. If you do have a kernel launch that takes place from the host, we will have a shadow breakpoint. And so you can insert a breakpoint on a symbol name that corresponds to a kernel launch. But we're going to insert it on the CPU side, and this will be inserted as pending. And once the Cuban is loaded, the address will be automatically resolved to the device location. We're also missing line info. So if you set a breakpoint in the middle of a kernel, you might see that it advances. The breakpoint is actually set at the end, and then once the Cuban is loaded, it will be updated. I'll go over this in an example on the following slides. So the behavior here is similar to the debugging experience of DLOpen. If you're familiar with DLOpen debugging, before you DLOpen a library, you don't have access to the symbols, and so once you DLOpen, then you have debug info. I also want to mention that C++ templates may result in multiple breakpoint locations. So a single template might be instantiated multiple times, and so you'd have multiple locations. So let's kind of go over an example showing this with pending breakpoints. So let's say I've run my application to main. So I just have the host side running. I have not loaded a Cuban yet. I set a breakpoint on matrix CUDA. So this is a matrix multiply example from the CUDA samples. You can see here, we set the breakpoint, but it's going to be at the shadow location because we haven't loaded the Cuban yet. So it's enabled. The breakpoint's enabled, but these locations are no, because it's a shadow side. And we have two locations because this is a template. So there's either the 16 or the 32 variant that we've instantiated. And you can see that this corresponds to a host side address. Then let's say we continue to the breakpoint. So we want to actually continue to the breakpoint on the GPU. So in the device code, if we hit the breakpoint, we issue info break to a second time. We can see here that we've hit the breakpoint and we have these two additional locations. And these two new locations are enabled and they correspond to device code addresses. So we automatically added locations to the breakpoint. Let's also talk about setting a breakpoint at file name line number. So here I set a breakpoint at line 104. You can see we set the breakpoint on two locations because again, it's a template. And then the addresses here are going to be all on the host side because, so let's rewind, pretend we haven't loaded the Cuban yet. And you can see here that the location has line number 129. So what happened was it found the next line in the line info, and that's past the end of the Cuban, which is line 129 on the host side. Once we hit breakpoint 2, so we've loaded the Cuban and we've resolved the breakpoint, you can see that this address has been updated. So now we have reset the address to line 104 and the correct GPU side address. So let's talk about stack trace. Some commands, these are the same commands that you use in GDB. So you can use where, BT, info stack, whatever you're comfortable with will work the same with device code. This applies to the CUDA thread in focus. So either CUDA thread or host thread that's in focus. So you can see an example here. I do a backtrace. We are focused on a CUDA thread, and we see that we made a bunch of different recursive function calls. So if you have function calls from your kernel, that will show up in the backtrace. But do note that CUDA threads, the first source line of the kernel will be the outermost frame. So frame number 3 in this example is where the kernel started. So we're not actually showing you where it was called from the device side, or from the host side, sorry. Examining state, I always like to start out with info locals. So this will show you all the local variables in your current stack frame. And either the value of the local variable will be printed, or a hint as to why the variable is not valid will be shown. So on the left here, you can see I issued an info locals. This was at a breakpoint at the start of a kernel launch. So if I do info locals, I see, oh, nothing is available. Why? Well, why is that? It's because these are all stored in registers, and the register is not live at this particular PC. So if I step through my application a few times, you can see that in the middle here. I'm issuing next commands. These registers are becoming live. So if I issue an info locals again a second time on the right, you see that the values have been updated. Print command, this is what most people are used to with GDB. This will allow you to read a source variable, and this works the same way with device variables. So, but the variable must be in scope, and this could be either local or global scope. So here's an example: print. I have an array A. Print element 1. Get the value of 1. You can also print the address. And it will show you the storage location here. So we're stored in generic memory, and it's a float pointer. And here is the address that we're pointing to. You can assign variables in your inferior. So if you use set variable, it will allow you to write a source variable. Do note that the address space must have write permissions. So if you are trying to write to read-only memory, this will not work. So as an example, print the value of bx, see that it's 0, set variable bx is equal to 3. This is a device variable. Now we've assigned it, and we can read it back and see that actually the assignment went through. Address, so you can supply address space identifiers when the storage space is ambiguous. I have a bunch of address, all of the address space identifiers are listed here that CUDA-GDB recognizes. Note that I'm not going to mention each one, but do note that it starts with an @ sign. That is how you specify an address space. Then you can use info registers to inspect device registers. So these are SAS registers. We use pseudonames here. So $R followed by the reg number is going to be a regular register. UR is uniform, UP is uniform predicate, and then of course PC, that's a program counter, but it is unassignable. So you can't assign to the program counter, expect your execution to advance to a different location. All right, let's talk about API errors. So if you want to track API errors, you can set the behavior with set CUDA API failures. This allows automatic checks of any CUDA driver or runtime API call. There's 3 modes that you can set: either hide, you don't want to report an error of any kind; ignore, you want to emit a warning but continue execution. This is the default setting. Or stop, you want to emit an error and stop the execution. So you can see here, if you set, I set CUDA API failures to stop, then I continue, hit an API error, and execution has halted, and I'm allowed to debug the inferior at that point. GPU exceptions. So device exceptions are always caught. These are traps that happen on the device. They're usually always fatal. So what I mean by that is you can't, if you encounter one of these that were generated from your application, you can't continue device execution. Most exceptions are precise. If you want to view the address causing the exception, you can use the convenience variable $errorPC. And if your application uses CUDA clusters, so this is a CUDA 11.8 or newer feature, cluster exceptions are in. So there's some new cluster exceptions, and these are imprecise. and if you want to find the exact PC that caused the exception, you don't have error PC in this case, but you can use the auto step feature to determine the exact block and instruction that caused the error. Auto step is going to do a step by until it encounters an exception, and it will halt the debugger right where the exception occurs. I'm not going to go into how to use auto step, but if you're curious, you can use help auto step, or you can read up on it in the CUDA-GDB documentation. We do recognize CUDA exception 0 through 18, and here's a link to the table. I did put it in the slide. I just wanted to mention that you'll see that in this table, there's a bunch of exceptions that are deprecated. Those only apply to older hardware, and we don't support that exception going forward. So you should treat that as device unknown exception, and it shouldn't be hit. All right, let's go through a full exception example. So this is what it would look like if your application hits an exception. You see warp out of range address. The exception was triggered at PC. We get a PC number. This is error PC, and we get a file name and line number. And then we see we're going to switch to the CUDA thread that caused the exception, and we see the signal CUDA exception 5. We're switching focus. And then we see that our PC is at line 44. So there's a little bit of slippage, and that can happen. When you hit an exception, you can have a little bit of slippage, so your PC will advance past the exception, and you can use error PC to see the exact instruction that caused the exception, and then you can look at PC to see where you're currently, where the control returned to the user. If you want to list the source line that caused the exception, you can do so by dereferencing the error PC convenience variable, and we can see it's at line 21. So you can see, oh, oops, the above line caused an out of range access to shared memory. Disassemble, this is used to view disassembly of SAS instructions. The current PC will be prefixed with an equal angle bracket, and the instruction, if there was an exception that occurred, the instruction triggering the exception, or error PC, will be prefixed with an asterisk angle bracket. If they match, you'll get asterisk equal sign angle bracket. So these are just some examples of what disassembly would look like. So you get a PC followed by the SAS instruction. All right, let's talk about Cordums. So we do support Cordums for GPU. These are disabled by default. If you want to enable them, you set CUDA enable Cordum on exception environment variable to 1, and then we will generate a Cordum when a exception is encountered. So here's an example. I've set that environment variable, run my app, and I can see that we have a Cordum that was created in my current working directory. The Cordum name by default is this string. So we have some percent identifiers here. %T is going to be the second since epoch. %H is going to be the host name of the system. %P is the process identifier of the CUDA application. Cordums are written to PWD by default if you don't specify the full path in the environment variable. So you have user-defined locations by setting CUDA Cordum file. We recognize those % sign specifiers, and here's kind of an example. So if I wanted to write a Cordum to a different location on Luster on Polaris, I could do so by generating this string. Lightweight Cordums. So if you want to enable lightweight Cordums, you set the CUDA enable lightweight Cordum environment variable to 1. When you do this, GPU Cordums will forgo dumping memory. So what I mean by this is you won't have local, shared, or global. So you can't really do much for debugging, but you will get you can see a backtrace. So you can see how you got to that location, but you can't examine program state. The size of the core dump here will be reduced significantly. Sometimes this is helpful if you just want to, if you just need to see a backtrace, you can use this feature. We also allow for user-induced GPU core dumps. So if you set the CUDA enable user triggered core dump environment variable to 1, we will open a communication pipe for each CUDA process. And when you write to that pipe, it will force a GPU core dump to occur. So you can see here as an example, set the environment variable, run this matrix mol app in the background. I then look for that core pipe file, echo 1 to it. So I wrote to the pipe, and then you can see that we're forcing a core dump to be generated. So this can be really useful if your application's hung and you don't know why, and you want to force a core dump to take place. So core pipe name by default is the string. We have the same percent specifiers as before. And you can set the CUDA Cordum pipe environment variable if you want to specify the location that the pipe is created. So let's talk about loading Cordums. So in CUDA-GDB, you use the target CUDA core command to load the Cordum for debugging. This will load the GPU Cordum into the debugger, and then you can debug it as usual. You can load both CPU and GPU Cordums. The CPU Cordum is optional. In this case, you don't have to specify, but that would allow you to switch between host and device focus. So you could use a thread command to switch over to a CPU thread, and you can use the CUDA commands to switch back to the CUDA thread. And something nice here is examining Cordums with CUDA-GDB does not require GPU to be installed on the system. So if you want to examine your core dump, say on the login node on Polaris, you can do so. You don't need it to have access to a GPU. All right, so that brings me to the end of the CUDA-GDB section. Looks like there's no questions in chat, so I'm gonna move right along to the Compute Sanitizer section. Unless, maybe is there, I'll pause for a sec. Are there any questions on the phone? All right, if not, we can continue on. So Compute Sanitizer, what is it? The Compute Sanitizer is a suite of dynamic analysis tools to catch common programming errors. So there's 4 tools that we support. There's MemCheck. This reports invalid memory accesses. InitCheck. This reports uninitialized memory reads. RaceCheck reports invalid concurrent accesses to shared memory, and SyncCheck reports on invalid barrier usage. The Compute Sanitizer is a non-interactive command line based tool. So what I mean here is you wrap your application with the Compute Sanitizer command, and it will run until it either encounters an error or the application completes. This provides proactive debugging of CUDA kernels. So it's a little different than CUDA-GDB in that regards, because you can discover common programming errors up front. So you might not even know that you have a problem in your code, and you can use the Compute Sanitizer to uncover some of these common programming errors. Again, we support CUDA, Optics, OpenACC, OpenMP, or any middleware library that will compile down the CUDA code. And I do want to mention that this Compute Sanitizer replaces the older CUDA MemCheck tool. So some people might be familiar with CUDA MemCheck. This has been deprecated since CUDA 11.5, and we're removing CUDA MemCheck in the next major release of the CUDA toolkit. And I want to mention that CUDA-GDB, we used to have MemCheck integration, and we've removed that support going forward. Instead, we're encouraging people to use the sanitizer core dump feature, which I'll talk about in a later slide. So on Polaris, the Compute Sanitizer is missing from path with the default NVHPC module. I had to construct this path to get at the Compute Sanitizer location, so I can set my path to point at this. I also saw that there was a newer NVHPC 22.7 module, which was non-default. And it would be with a mismatched driver. So you'd be running with the older driver, but a newer CUDA toolkit, which works in many instances. So if I loaded that, then I did have Compute Sanitizer in my default path. So again, we want to recompile for debugging. So this will give you the best experience. So again, minus little g for host and minus capital G for device. This will give you the most verbose error messages. But you can use line info in this case to allow checking of optimized code, but you could encounter reduced quality of your output messages. Here's a link to the latest documentation. We have a Compute Sanitizer form if you need help. And then there is a link here to GitHub Sanitizer examples. I see that there is a question. I'll switch over to this question in the chat. Alfred Tang asks, is there an alternative to CUDA-GDB? That's a good question. In terms of NVIDIA, we just provide support for CUDA-GDB. There are other tools out there in the HPC world. So I believe HPE supports a parallel debugger called GDB for HPC, which does have integration with CUDA-GDB. And then there's also third-party parallel debuggers. So there's TotalView, and then also Forge, which is an ARM tool. I'm not sure if those are available on Polaris or not. But I did check. GDB for HPC is available on Polaris. All right, so back to Compute Sanitizer. So the first tool that I'll talk about is MemCheck. So MemCheck is used to report invalid memory accesses. So things like if you have out of bounds or misaligned read-write atomic accesses, and this can be of local, shared, or global memory. Stack overflows, invalid system scope atomic accesses. So this is a lesser known one. So if you have a peer access over NVLink, we can detect invalid atomic access to the peer. There's reports for CUDA API errors, hardware exceptions, invalid device-side malloc free usage. So for instance, if you have a double free, the tool will detect that. And this is the default tool for Compute Sanitizer. So if you start Compute Sanitizer without providing a tool option, you get MemCheck by default. So let's go over a quick example. On the top left here is just a simple error that we've introduced. So you can see in main, we're allocating a device buffer of 31 ints. Then we're going to fire off a kernel with 32 threads. And each of those kernels are going to write into the buffer that was passed in at its thread index the value of its thread index. So oops, we've written off the end because we only have 31 ints in the buffer and we have 32 threads. So when you run this under MemCheck, you can see I type Compute Sanitizer and then the name of this program. So I compile the MemCheck test. The output I'll see is invalid global. So the type of address space right here was a write to a global address and its size of 4 bytes. And then we see the PC and the line number where the write took place, followed by the thread. So again, we index from 0 to 31. So this is the element 32 in the array, which doesn't exist, and it's out of bounds. So we wrote right off the end of memory, and we see the full stack frame. We do tear down, so we destroy the CUDA context by default on the first error when we encounter it. So you can see here we're encountering a launch failure and then the application exits. You can control this with command line arguments. So if you say destroy on device error to kernel, it would only destroy the kernel, but it would allow you to continue execution. So maybe you could get a little further to get multiple errors out before the inevitable crash occurs. We also have support for reporting device-side memory leaks. So if you say leak check is full, so in this case, I fixed the problem, even though it's not shown in the code here. If we do CUDA malloc to say 32 instead and run with leak check full, we would see that we've leaked 128 bytes. So what does that mean? Okay, we have a CUDA malloc, but we don't have a corresponding CUDA freeze, so we should go fix that in our code. And what's nice about Compute Sanitizer is when you fix things, you can rerun a second time to verify that you've actually fixed it. So then the error goes away after you recompile. Something that's really useful too is you can avoid false negatives of invalid memory access with padding. So there's this padding argument and then the number of bytes you want to pad with. This will add a padding buffer at the end of each allocation. So sometimes you can have sequential allocations that abut right up, that they're adjacent to one another. This will ensure that there's padding at the end. So any memory access that reads off the end, instead of accidentally reading this valid into the next allocation, which is a valid read from the sanitizer's viewpoint, you could add this padding section, which is a red zone, which then will say, oh, nope, you cannot read into that. That's invalid access. So you can avoid the false negatives. The next tool is initcheck. So initcheck is used to report uninitialized memory reads. These could be uninitialized memory reads involving the kernel, or it could be from memory you've passed to CUDA API calls. We only track global memory in this case, so we don't have support for tracking shared or local memory. But you can also track pure GPU allocation. So if you have an allocation that occurred on a peer and then passed to a different peer, we can detect uninitialized memory reads. So here's a simple example on the upper right. we allocate a array of 32 ints, and then we're going to fire off a single thread in the kernel. We're going to assign into this buffer that was passed in at our thread index the value of the buffer at our thread index plus our thread index. So you can see here, we're reading from the buffer, which we never set, so it's uninitialized. When we run this, so here we're saying Compute Sanitizer, we're going to specify the tools and MemCheck, run with our 8.out that we compiled. We see an uninitialized global memory read of size 4 bytes. And again, it gives you the source file and line number, the thread that caused the uninitialized read, and then the full stack trace. And another useful tool or a useful part of MemCheck that you can use is you can track your unused memory allocations. So what I mean by that is global memory that you've allocated but never actually written to. If you pass the track unused memory option equals yes, we will track that allocation. So you can see on the upper right, again, it's the same code as before. We're allocating 32 ints, but we're only going to use one of them, so that the tool is able to say, oh, you have uninitialized memory in allocation, is the address of the allocation of size 128. We didn't write 124 bytes. So that's 96.875% of our allocation went unused. This can be really useful if you're kind of running into memory limits on your GPU device and you want to figure out how to cut down on memory use. You can use this tool to do so. Race check. So we use this to detect potential race conditions. So write after write, write after read, read after write hazards to shared memory that lack valid synchronization primitive. This could either be a warp or block level synchronization primitive. So if you don't have synchronization between these accesses, the tool will detect that error condition. We only support this for shared memory. Global and local memory are untracked. And then there's two reporting modes. The first one is analysis, which is an aggregated report. So we'll aggregate like messages into just a single entry. And then the second one is hazard. So here, every detected error will be printed with details. It's very verbose. You'll get lots of information, but sometimes you need that to fix your race condition. So here's an example on the upper right. So we have a buffer, 64 ints. We're going to fire off a kernel with 64 threads. And you can see here that the kernel will have a shared array. We're going to write into the shared array at our thread index, the value of our thread index. And then we're going to write into the buffer, the global buffer that was passed in, the value of our peer shared entry. So we're saying our thread index plus 1. That's a race condition because we're reading and writing at the same time without any sort of synchronization primitive. So when we use the default mode, analysis mode in Compute Sanitizer, with race check, you can see that we get a single error message printed. So we have a race reported between write access at a PC line number, so at line 5, followed by a read access at line 6, and there was 256 hazards detected in total. Here we're on the second green box. We run with hazard mode, so we're passing race check report is equal to hazard. And you can see where I'm just looking at the first entry, but there's a lot of additional info. So this could be useful, but most of the time it's best just to start with the aggregated output just to see what comes out. And then if you need to add in the hazard mode. All right, finally, SyncCheck. This is the last tool. This is used to detect invalid use of CUDA synchronization primitives. The behavior here will depend on architecture, but you can detect things like invalid divergent threads in a warp or block going into a synchronization primitive, or invalid barrier arguments, things of that nature. So as a cool example, there's a newer feature called CUDA Barrier. This is a lot like standard barrier in C++20, if you're familiar with that. So we're creating a CUDA Barrier And here we have to define how many threads we expect to arrive. So when we're initting it, we're saying block_dim.x divided by 2. So that's where our error is. We don't have enough. Too many threads will arrive into the barrier. So we have async threads, and then the barrier action takes place afterwards. So if we run this under the sync check tool, we'll see that we have a barrier error detected, barrier overflow. Again, our source file line number, and it's at the arrives. So oops, we did not size this barrier to the correct size. Let's go over some useful options that you can pass to the Compute Sanitizer. So these are command line arguments that you can pass. If you want to track all of your child processes, you can use target processes equal to all. If you want to filter kernel launches, the desired kernel launches that you want to be tracked, you can use kernel regex or kernel regex exclude. You can track or ignore n kernel launches. So if you want to just track the first n launches, you can use launch count, or if you want to skip a number of launches, you can use launch skip. You can force stream synchronization every n launches with the force synchronization limit argument. And you can also have XML output if you want to do some post-processing in XML. Now let's talk about the Cordum feature. So if you pass the argument generate Cordum is equal to yes, that means that on the first error, we're going to emit an entire core dump that you can then take and debug with CUDA-GDB. So that gives you a full debugging experience. So if you really need more info, maybe you don't know what local variables played into that error, you can do so with the core dump. We don't support core dumps for the race check tool. I also want to mention too, if you're using a library that has a custom memory allocator, we do have support for Compute Sanitizer using the NVIDIA tools extension, or NVTX. I'm not going to go over that, but if you follow the documentation, we have full examples on how to make use of that. So that brings me to the end of my material, and I'll open the floor for any questions or comments that you guys might have on either of the two